Yes, students, can you hear me? Okay. So you can take a couple of minutes break, 2 minutes or 3 minutes, because you had two consecutive lectures. So after 2 minutes, I will start. Okay. So now I'll start. Uh, can you see the slide? Please type in a chat box. Okay. Okay. And am I audible clearly? Okay. So today's topic is last topic of AES. So we will end up AES today, and we'll also cover some other mode of operation which are used for applying AES and DES, both algorithms. So first, the basic AES mechanism which we discussed till now, that is the process. The basic process involves sub-byte. Okay, each round contains sub-byte, that is substitute byte, shift rows. These two operations you have to remember. We used to perform substitute byte. For that, we used Galileo's field, and we used this Galileo's field concept for finding substitute byte. And then shift rows, then mix column, and add round. So this was the basic, and each round. So the steps involved in round are discussed, and basic AES includes round 1, round 2 up to round NR plus one pre-round, right? So one pre-round plus NR rounds. If it is 128 key size, then the number of rounds are 10. If 192 is the key size, then number of rounds are 12. And if key size is 256, number of rounds are 14. So you can see that here this key expansion is used, right? So here we have a cipher key of 128, 192 or 256 bits. From this one key, the key expansion ensures K0 to KNR. So total NR plus 1 keys. Okay. So this, we will talk about this key expansion. Okay, this particular key expansion. So as I said that to create each round keys for each round, AES uses this key expansion process. Now, if the number of rounds are NR, the key expansion routine creates NR plus 128-bit round keys from one single 128-bit cipher key. Okay. So size of cipher key is 128-bit. 128-bit, if we divide it by word size of 32, then we get 4 words. Please understand this. 128-bit is the size of key. Size of word is 32. So how many words you get? 128 divided by 32, right? 128 divided by 32, right? So size of word is 32, right? Each word is of 32 bits. We perform the operation in each round for a byte. What is the size of a byte? 8 bits. So here we are talking about operation on word, which is 4 times the size of byte. So we can say our key, so total 128 bits. So how many bytes are there? Can you calculate? How many bytes are there? Total 128 bits. So how many bytes are there? 16, right? So here we have numbered those 16 bytes, K0, K1 up to K15. So you can see that this is our first key, okay? And it is represented as bytes. It is represented as 16 bytes. It is numbered as K0, K1, K2, K3 up to K12, 13, 14, 15. Okay. Now this is our first key and it is given to pre-round. Like I had shown you here. This is pre-round and it uses K0. So considering that this is our K0, yes. I am getting some disturbance from some of you. So please turn off your mic. Okay, understand this concept well. These 16 bytes are making first key, which is applied to pre-round. And for other keys, we have to generate by this process. So I will explain you this process now. So in this process, if you look at this, W5. How do we get W5? W1 XOR W4. Then we get W5. W1 is 32 bit. W4 is also of 32 bit. So if we do XOR of these two, we get W5. Is this clear? Is it understood? W8. Suppose we take W8. Then W8 is different. Here, its previous W is not available. So we have a different block here, which is called as T8. So if you look at this W5, W6, W7, W9, W10, W11, W41, W42, W43, this block is dependent on two previous words. One is I minus 1. If we say this is Wi, then it is I minus 1 XOR I minus 4. Please check this formula Wi minus W4. Understood? Wi minus XOR Wi minus 4. Got it? Understood how we obtain all these blocks? Right? So we can write this general formula. If I, for I equal to 4 to 43, 4 to 43, this to this. In this, these blocks 5, 9, 41, they are I mod 4 not equal to 0. So if I mod 4 not equal to 0, then Wi is 1 less than I XOR 4 less than I. So 2W, previous W, Wi minus 1 and Wi minus 4. That generates this Wi. But if you look at these W's, W4, W8, W40, which means Wi mod 4 equal to, what will be the I mod 4 here for all this block? Yes, Priyank, but others? Any other student? Can you please answer? Okay. Only Priyank is answering. Is it Priyank's class only? Or you are also participating? Please participate. Okay. So let us see how do we obtain this W4, W8 and W up to W40. So if I mod 4 equal to 0, then we have to follow this process. Now this process includes rotation of word, substitution of a word, and R constant. Okay. So we want to perform W4. We want to get W4. For that, one previous W is available, that is W0. But this second T4 is not available. So we have to obtain this T4 by applying this process where Wi minus 1, okay, Wi minus 1, it rotates the word. Rotation of the word is like a shift register. We had seen here, right, in this shift rows, right? So in here, shift row means shift the whole word, right, by bit. So shift rotation word means the operation is applied on byte. on a word. So that means 32 bit. Then it is followed by substitution of a word. So substitution of word is similar to this. Here substitution of byte. So here we have substitution of word. Okay. So by applying shift and substitution of word, we XOR that value with our constant. So these are some constant. I will show you what these constants are. So when we do XOR, we get Ti. So here we have T4. So T4 is equals to W3, rotate the word, substitute the word with 3 by 4 by 4. So R constant 1, I equal to 4. So 4 by 4. So R constant 1. So W4 is W0, I minus 1 means 4 minus 4. Right? So W0 and T4. So this one is T4. So T4 XOR W0. Each W is a word. So we have initially W0 to W3, and from that we are generating W4 to W7, W8 to W11, W40 to W43. And each row of 4 Ws, that indicates one key. In the equation of Ti, yes. So in the equation of, you mean this one? So Wi is equal to T. So where? In this diagram? Yes, Priyank, you can. This one? So making of Ti words, so I is equals to 4 into NR. NR means what? Number of round, right? So how many rounds you have? 10 rounds, right? So 10 rounds means 40, 10 into 4, 40, right? So we need 4, 8, 40, right? So it is multiplied by 4 into 1, 4 into 2, 4 into 10, 40, right? So we need these keys not for the first, because here we already have a key. But here we don't have a previous block. And that is why we take temporary word, which we obtain by following this process. Understood? Understood? Priya? Okay, so 4 word means 32 into 4, 128 bit. Okay, so this is the formula for I mod 4 equal to 0, Wi equal to T XOR Wi minus 4. If W4, that means T XOR W4 minus 4, that is 0. And here it is T4, right? So you see T4 W0. For 8, I equal to I mod 4. So I equal to 8. 8 mod 4 equal to 0. So W8 equal to T8 XOR W8 minus 4. So W4, right? And T at that time is T4 is T8 is substitute word, rotate word. First do rotation, then do substitute. Rotation of W7, 8 minus 1 W7 XOR with 8 minus 4, 8 divided by 4. So 8 divided by 4 is 2. So R constant 2. Understood this? Right. So rotate word is similar to the shift rows, but it is applied to the byte. And sub word is similar to sub byte transformation, but it is applied to the bytes, 4 bytes or word. Now round constant are these. Round constant 1, 2, 3, 10. Okay, we need 10 round constant because we want to generate 10 keys. Okay, so here we need 10 round constant. I equal to 1 by 4. Sorry, I equal to 4 by 4, 8 by 4, 12 by 4, 16 by 4, 20 by 4, right? So we get R1, R2, R3, R4, R5. So it is straightforward. Up to R1 to R7, it is straightforward. How do we get this value? It is very straightforward. Let me show you. So this is our round constant. Okay. So it is as per this formula. It is obtained as per this formula. RCI is equals to x raised to I minus 1 mod x raised to 8 plus x4 plus x cube plus x plus 1. Now this polynomial, as you know, it is Galileo's field, right? So we will apply the same method, x raised to I minus 1 mod this. So if it is RC4, that means we have x cube I equal to 4, 4 minus 1, 3. So it is x cube mod this. X cube means what? X cube means, how do we represent it into binary? X cube. So x raised to 0 is 0. X raised to 1 is 0. X raised to 2 is 0. And x raised to 3 is 1. Yes. So this is equal to 8, right? So our first value is so our RC4 is 8. Okay, see this 8. Can you see this? Okay, except Priyank, anybody else has understood this? Okay, okay. Right, so up to this, it is straightforward. But let us consider this 9, 10, RC10. So for RC10, we have x raised to 9 mod this. So we have to apply this formula because we cannot find straight away this. So we have to apply this. So x raised to 9 divided by this polynomial. So we multiply it by x. So x raised to 9 gets cancelled out, and then we have this remainder. So this remainder x raised to 5 plus x raised to 4 plus x square plus x, that is represented by the number in binary by or in hex by 3, 6, because x raised to 5 is 1, x raised to 4 is 1, x raised to 2 is 1, and x raised to 1 is 1. So it becomes 0, 1, 1, 0, and it becomes 0, 0, 1, 1. So this is 3 and this is 6. So RC10 is 36. RC10 is 36. It is understood now how we have found this number. Very straightforward and easy, right? So this is about key expansion. Now AES, its security analysis we will do. So there are 3 aspects of the AES security analysis. First, what will happen if we apply brute force technique? So in a brute force technique, we have 128-bit key. So the total number of possible keys are 2 raised to 128, which is very large number. So it is practically not possible. But suppose if we can break DES in T second, suppose although DES itself is difficult to be broken because DES uses 56-bit key, but suppose if we take that number, okay, suppose we are able to crack DES with T second, and let's say we take T equal to 1 second. So what will happen? DES takes 2 raised to 56 key T seconds, T equal to 1. So it takes 1 second. Okay, we are assuming theoretically that DES can be encrypted, can be broken in 1 second. So how much time it will take for 2 raised to 128 keys? So if the DES is having 2 raised to 56 bit and AES has 2 raised to 128 keys, then 2 raised to 128 divided by 2 raised to 56 into T. This is equal to 2 raised to 72 into T seconds. Now, if T equal to 1, then also 2 raised to 72 is huge number in terms of second, which indicates thousands and more than that years, which is practically impossible. So brute force is not possible. Statistical attack is also not possible because we use strong diffusion, confusion, because we use substitute byte, Galileo's field, shift row, mix column, right? So all this creates so much confusion and diffusion properties, so that statistical attack is not possible. So brute force not possible, statistical not possible. Differential and linear attacks. So there are some people who have theoretically suggested ways to break this AES. However, no practical situation has occurred in which AES is broken. Okay. So this is only a theoretical part. Nobody has practically done the cryptanalysis of this AES algorithm. That is why it is very popular and useful in the industry. Another thing is regarding the implementation. It can be implemented in the software or it can be implemented as a hardware. So you can have a system on chip. There is a term called system on chip, embedded systems. These are basically pure hardware which are used for encryption purpose and decryption purpose. So there are dedicated hardware, okay, and there are also firmwares which uses this DES AES. So basic, and it is possible to implement both on software, hardware, and firmware because its basic data type is either byte or a word. That is why, right? And it is very simple and cost effective. Okay. So cheap processor means you don't need high-ended processors. You require very comparatively less costly microchips. Okay. That is semiconductor. That is with the help of semiconductor technology. All right. So this ends our discussion about AES. Now I am starting chapter number 8. This is modes of operation. This is chapter number 8 in the textbook by Forosan and Mukhopadhyay, Cryptography and Network Security. And I will finish this chapter today. So please pay attention. Now this is more about applying AES and DES. Okay. As you know that block ciphers encrypt the fixed size block, like DES is 64-bit block, right? And AES uses 128-bit block, right? So in practice, what happens? We may not have blocks of this size. So in that case, we may not be able to use this DES and AES because AES and DES are applied over block. So we have to apply this DES and AES DES or AES, for our plain text, which is not in the form of block, then we have to apply these modes of operation to use these existing DES and AES blocks. Okay, and there are 5 popular modes. First is electronic code book mode, cipher block chaining mode, cipher feedback mode, output feedback mode, and counter mode. So first we see electronic code book mode. This is more about the design, how these are designed, right? So we want to apply DES and AES for plain text, right? So how we can apply this on different modes. So first mode is electronic code book mode. So in this, plain text is divided into blocks of appropriate size. So you can see in this diagram, the plain text. So we have block of encryption. You can see this is a box, which is encryption block. And we create these blocks of plain text, which can be applied on this encryption algorithm. This E could be DES or AES, anything. So we have to create blocks accordingly. So suppose we create PM, P1 to PM plain text block, and we use the single key K. So we generate cipher text, right? So we generate C1 to CM blocks. So if we apply this method of encryption, it is possible that some plain text blocks are identical, because it is possible in the plain text that certain plain texts are matching, right? They are identical even at the time of transmission or encryption. So if the plain text is identical, cipher text block will be identical. That is the limitation of this block mode. So here we have encryption algorithm and we have cipher key, and that generates M cipher blocks. So this is the basic diagram. Okay, and you can have a hardware implementation of this, where these blocks are created fixed. Right? See, what we have to do is we have to create blocks of plain text. Plain text. Suppose if it is plain text is 64-bit, then we create one block of 64-bit, and correspondingly we generate C1. Then we take another block of 64-bit P2. Then we generate C2. So we keep these blocks ready, and whenever we find we want to perform transmission, we look at, compare it with P1, and instead of doing encryption at that time, directly we can take encrypted block from that available code book. That is the basic concept. Okay. So decryption is straightforward. Similar to the encryption method, we have decryption algorithm. So C1 is applied this key and it generates P1. But the limitation, as I told you, that limitation is that if two plain text blocks are identical, then corresponding cipher text blocks are same. And it happens because repeated text segments at block boundaries are encrypted to same ciphertext. This will make it possible for cryptanalysts to break it. So if we get encrypted block and if we can match it, then we can easily decrypt it. Right? So cryptanalysis is possible. So this is actually not a good way. It is prone to cyber attack. So second mode is used where the plain text and ciphertext will not be identical. So if two plain text blocks are identical, ciphertext block will not be identical. And look at the design. It is called as cipher block chaining. It is a chain which we are creating. See, what happens is, in this mode, we have a plain text P1. You can see that is XORed with some IV. IV is initialization vector. Okay. So instead of directly giving P1 to encryption, we first XOR with initialization vector, and the output of it that is given to encryption and key. So this output P1 XOR initialization vector encrypted with key, and then C1 is generated. That is ciphertext block 1. Now this ciphertext block is given here as an initialization vector to P2 for performing XOR operation. Okay, so we have C0, which is initial vector, and this is supposed to be known by both sender and receiver. Okay, so it is actually transmitted secretly, right? So we have to ensure that the transmission of this initial vector is secure. So this is actually creating a chain, right? So P2 XOR C1, that the output of that goes to encryption with key K, and it generates C2. C2 XOR P3, that generates encryption, that generates input for the encryption block. So if we write it mathematically, we can write C0 is equals to initial vector, and all other C's can be computed like this: Pi XOR Ci minus 1 for I equal to 1 to M. If P1 XOR C1 minus 1, that is 0, P1 XOR C0, that is encrypted with K key, it gives us C1, right? Let's say C8. So to get the I equal to 8, we have P8 XOR C7, P8 XOR C7 encrypted with key Ki, and that gives C8. Okay, so the decryption is also possible, like this is our encrypted text. To perform decryption, we apply decryption algorithm. So D of Ci with K key is equals to D of EK Pi XOR Ci minus 1 with K. Now this gets cancelled out. So on the right hand side, we have Pi XOR Ci minus 1. And on the left hand side, we have D of Ci with K. So if we do XOR Ci minus 1 on both sides, this will be cancelled out. So on the, and we will obtain Pi. So Pi is equals to D of Ci with K key XOR Ci minus 1. Understood? So the encryption is resulting into decryption also, right? So we can draw the diagram like this. So here what we have done, to get the decryption, we have to go in reverse. Okay, we have to go in reverse. So C1 goes an input to decryption with K key. The output of that goes to XOR for initial vector, and this generates P1. So if you see the diagram, C1 goes to D with K key, which generates some intermediate plain text. That intermediate plain text is XORed with initial vector. And remember that initial vector is shared secretly between sender and the receiver, and that generates plain text P1, right? Now, for the second value, we will give this ciphertext C1 here, right? So C2 and key K is applied on the decryption block. The output of this intermediate plain text is XORed with C1, and that gives us plain text P2, right? So it is as per this formula, D of CI, D of suppose P8. So if we want to obtain P8, so we have to decrypt C8 with K key and XOR it with C7. So previous cipher block we have to take. So this is a chaining, and it helps in solving previous mode problem. Even if P1 equal to P2, it is not necessary that C1 is equal to C2, right? Now why? Because in chaining we are doing XOR. So here we are doing XOR. So it will definitely change it, right? XOR of Pi with Ci minus 1, which causes Ci minus 1 and Ci to be different. But there is a problem with this mode. The problem is that if there is an error in block Cj, then it will be propagated to all subsequent blocks. Like for example, there is an error over here, then it will be propagated at all places, right? Because it is a chain. So here also, if suppose there is an error in C1, so C1 goes to P2 and then it is creating C2. So if there is an error in C1, it will be propagated in C2. It will be propagated here also. And so correspondingly, the errors will be propagated here also. So to solve this problem, we go for the third mode. So the third mode is cipher feedback mode. So far, have you understood whatever I discussed? Both the modes are understood? Please respond. Electronic code book and cipher chain, cipher block chaining. Understood? Please type in a chat box so that I can proceed to the third block. Yes, students. Okay, it is relatively easy, but pay attention to understand this third block. It is little bit tricky. Now see, the problem with the previous mode is that error is propagated to subsequent blocks. So to solve that problem, we have another method that is called as cipher feedback mode. So here we use one shift register, and instead of encrypting plain text, we encrypt shift register. Okay, so we take some initial vector which is of size n bit. Remember, this cipher feedback mode is applied when we have plain text of size r bit and r is less or equal to n. Suppose our block size is of n bit, but our plain text is of r bit, r is less than n. Then we can go for this mode. Okay, so what happens? We take initial vector of n bit and then we apply encryption over this n bit initial vector with the help of key, because these two are matching, so it will generate encryption. So encryption of n bit. Up to this it is understood. Up to this, some initial value of n bit is taken. Up to this, It is understood? Please type. It is very important mode. Please type in a chat box. See, instead of plain text, we are taking initial vector that is of size n bit. Okay, and key is of n bit, and we apply encryption algorithm, and that generates n bit of encrypted bits. But this is not our plain text. This is shift register. Understood? Okay. Now these n bit are divided into two sections. First section is of r bit. Suppose this is n equal to, let's say, 64, but our plain text is 8 bit. So 8 bits are taken from this 64, right? So 64 minus 8, 64 minus 8, that is 56 bits are n minus r. So we will take only 8 bits from these encrypted bits. Understood? Understood? And we will XOR it with plain text of r bit. So our encrypted bits are XORed with r bits of plain text, and it will generate r bits of ciphertext. Understood? Understood now? Okay, now see what happens. This is very interesting. Now shift register is shifted left side. See, this is first operation for P1 and C1. For second operation, we need this, right? So what we do, we perform shift operation on shift register, and shift register is shifted left side by r bit. So if we shift r bits to the left, on the right hand side, it will generate r bits of zeros. This is known fact to all of you, correct? We have shifted r bits to the left. So right hand side, we have r zeros. Understood? This is based on your left shift operation. Okay. So these r zeros are created. Now these r zeros are replaced by previous ciphertext C1. See, this is C1. So this C1 of r bit is put here with this n minus r bits. Okay. So what happens? This becomes our new shift register. Understood? New shift register. So this is first operation. For second operation of shift register, we will left shift by r bit. Those r bit are replaced by this C1. So we will have new content of this shift register, which is applied for the second round. Okay. So what happens? Now new shift register, K key, encryption, n bit, take first r bit with P2 r bit, XOR it, it generates C2, again give it to the shift register where it performs r bit left shift, last r bit are zeros, replace it with this C2, and this gives again P3, C3. Understood this process? Yes, please respond. Okay, so this very important mode, all of you remember, this is cipher feedback mode, a very important mode. Now, this this mode can also be used as a stream cipher. You understand block cipher and stream cipher, right? So if R equal to 1, then it becomes bit stream cipher. If R equal to 8-bit data, then it becomes character stream cipher. And we had already discussed earlier in the first sessional initial lectures what is block cipher, what is stream cipher, right? So here we are talking about that stream cipher. So this mode of operation is more suitable for stream cipher. Okay. So here encryption and decryption process generates CIs, PI, but at receiving side, there is no separate decryption process, right? The advantage is that we don't need to create a new process, right? We need to generate encrypted output at the receiving side too. So see what happens. See, at receiving side, we have initial vector, key, encryption. Up to this block, it is same. Then instead of P1, we have C1 and XOR it with this. So it gives P1, right? Now this block, dotted circle, that is common at both ends, receiver and transmitter. So sender and receiver both can implement this as a hardware, and only you have to do the XOR operation because this is pre-computed. So you can do these all steps in parallel also. So that is the advantage. But the problem is that there is an error propagation which is high. So this mode should not be used where the error rate is high. Okay. So when the error rate is high, and which happens usually in the satellite communication, we use this fourth mode, that is output feedback mode. And it is similar to this, right? Here, what happens? Instead of C1 replacing the R zeros, these R bits are directly replaced here. So the transmission error will not take place. Understood? See what happens here. Here we are taking this C2 and putting it here, replacing it with these R zeros. So if there is a transmission error over C2, this will create a problem. But if we take this R bit, then this portion is common at both sides. So this R bit is going to be used over here. This is called as output feedback mode. And the advantage is that, so here you have initial vector key with encryption, R and NR minus N minus R. So R bits are used for next or updating the shift register value. And that gives, so P1 XOR C1 with P1 XOR R with gives C1. So the advantage here is that the error propagation will not take place. And it is very useful in satellite link communication. Okay, this is very important. And the last mode is counter mode. This is similar to here, but instead of initial vector, we have counter values. So it is more simple than this. Here we use this R bit and replace it. Instead of that, what we do? we take counter. Suppose this is 10, this is 11, this is 12, right? So we create a counter, and different counter values are used as an initial shift register value that is encrypted with key K, and then P1 XORs that output generates C1. Okay, and this can also be implemented parallelly. So parallel implementation is possible. Okay, so this ends chapter 8. Remember, this is chapter 8. Chapter 8. Okay, I have finished this chapter 7 and chapter 8. So next lecture we will have more interesting things. Okay, so any doubt, any question if you have from the discussion which I have carried out? Okay, if you don't have any question, then if it is your last lecture for today, you may leave then.